Pulmonary circulation starts with oxygen-poor and carbon dioxide-rich blood in the right atrium that flows into the right ventricle. From there, blood is pumped into the large pulmonary trunk, which splits to form the two pulmonary arteries, one for each lung. The pulmonary arteries divide into smaller arteries known as pulmonary arterioles, and then eventually into pulmonary capillaries which surround the alveoli, which are the millions of tiny air sacs where gas exchange happens. At that point, oxygen enters the blood and carbon dioxide enters the alveoli. The pulmonary capillaries drain into small veins known as pulmonary venules that flow into two pulmonary veins exiting each lung. And these pulmonary veins complete the circuit by delivering oxygen-rich and carbon dioxide-poor blood into the left atrium, which flows into the left ventricle and then into the aorta where it enters systemic circulation. Normally, about 2% of the blood follows a slightly different path. It's diverted or shunted so that it bypasses the pulmonary capillaries. And this is called a physiologic shunt. There are two main ways this happens. First, when blood goes out to the heart muscle itself, it returns through tiny veins called Thebesian veins. Rather than draining into the venous system and going into the right atrium, these veins sometimes dump that blood into the closest chamber of the heart. So, for example, if blood that goes out the aorta and through the coronary arteries to the muscle in the left ventricle of the heart, then the deoxygenated blood might then drain directly into the left ventricle chamber of the heart. At that point, it would mix with the rest of the oxygenated blood and get squeezed right back out through the aorta. So this blood basically bypasses the pulmonary circulation. Second, the conducting airways of the lungs, like the bronchi, receive systemic arterial blood from the bronchial arteries. But the deoxygenated blood can flow, or anastomose, right into nearby pulmonary veins which are carrying oxygenated blood that has already traveled through the pulmonary capillaries. So once again, deoxygenated blood might flow right into the pulmonary veins and mix in with the rest of the oxygenated blood, bypassing the pulmonary circulation. Now, in addition to these naturally occurring physiologic shunts, there are also some pathological defects that can lead to more shunting of blood. In most left-to-right shunts, blood flows from the left side of the heart to the right side of the heart. This can happen when there's a gap in the wall, or septa, that divides the left and right chambers of the heart. So, for example, a ventricular septal defect allows blood to flow down its pressure gradient from the high-pressure left ventricle into the lower-pressure right ventricle. And an atrial septal defect allows for the same thing, only blood is shunted from the left atrium to the right atrium. Another type of left-to-right shunt happens with a patent ductus arteriosus. The ductus arteriosus is a fetal blood vessel that creates a pathway for blood to flow from the pulmonary artery into the aorta. During fetal development, this is important because the lungs are not working and are fluid-filled and compressed. So oxygenated blood coming from the placenta bypasses the lungs and goes directly into fetal systemic circulation. This pathway is supposed to close at birth and allow blood to flow normally from the right ventricle into the pulmonary artery and into the lungs. But in some babies, it remains open, or patent, and that allows blood to flow from the high-pressure aorta into the lower-pressure pulmonary artery. The end result of any of these left-to-right shunts is that oxygenated blood is making a second loop through pulmonary circulation, which means that the right ventricle is doing a bit of extra work, moving blood around that's already oxygenated. On the flip side, in a right-to-left shunt, blood flows from the right side of the heart to the left. Normally, this wouldn't happen, because blood would not want to flow up its pressure gradient. But right-to-left shunts typically involve changing pressures in the chamber of the heart, which reverses the gradient. So, for example, in the congenital heart condition called tetralogy of Fallot, there's a large ventricular septal defect and stenosis, or narrowing, of the right ventricular outflow tract into the pulmonary artery. The right ventricular outflow tract stenosis increases the resistance to blood going into the pulmonary circulation, and that increases right ventricular pressure. If the right ventricular pressure exceeds left ventricular pressure, then blood can flow down the new pressure gradient, and a right-to-left shunt happens. Another example is Eisenmenger's syndrome, which is caused by pulmonary hypertension. Basically, what happens is that pulmonary hypertension, which can result from a left-to-right cardiac shunt, can get so severe that the pressures on the right side of the heart exceed the pressures on the left side, leading to a right-to-left shunt. Ultimately, in a right-to-left shunt, oxygen-poor and carbon dioxide-rich blood mixes with the oxygen-rich and carbon dioxide-poor blood that's already gone through the pulmonary circulation. The mixing causes oxygen levels to fall in the arterial blood, leading to hypoxemia. And supplemental oxygen does not bring levels back up because the blood going through the pulmonary capillaries is already saturated and can't pick up any more oxygen in the short time that the blood is going through the pulmonary capillaries. On the other hand, if there's even a slight rise in carbon dioxide levels, it's detected by central chemoreceptors in the brain, which promptly increase the respiratory rate. Carbon dioxide in the alveoli and blood equilibrates about 20 times faster than oxygen. So unlike oxygen exchange, which is physiologically maxed out, any excess carbon dioxide can quickly diffuse out of the blood and return to normal physiologic levels. In fact, it's the decrease in oxygen levels that can actually be used to calculate the amount of blood flow through the shunt, in liters per minute, using the shunt fraction equation. Mathematically, if the total amount of blood flow, or cardiac output from the left ventricle, is QT, then it equals the amount that's shunted, or QS, plus the amount that goes through the pulmonary capillaries, or QC. Based on this, the shunt fraction is the proportion of blood flow through the shunt over the total blood flow. Similarly, the oxygen content in the cardiac output, which is the arterial blood, or CaO2, is equal to the oxygen content of the blood flowing through the shunt. And remember that it's venous blood that's diverted through the shunt, or CVO2, plus the oxygen content of the blood flowing through the pulmonary capillaries, or CCO2. Now, the more blood flow, the more red blood cells there are to carry oxygen. So oxygen content is affected by blood flow, and we can multiply QT by CaO2, QS by CVO2, and QC by CCO2. Now we can arrange the total blood flow equation to substitute QC with QT minus QS. Now, the goal is to solve for QS divided by QT. So we can first distribute CCO2 to get QT multiplied by CCO2, minus QS multiplied by CCO2. Now, let's get all of the QS parts of the formula on one side of the equation, and all QT parts on the other side. Next, we can factor out QS to get QS times CCO2 minus CVO2, and do the same thing to QT to get QT times CCO2 minus CaO2. Now we divide both sides of the formula by QT, crossing it out from the right side, leaving us with QS times CCO2 minus CVO2 divided by QT. And then divide again by CCO2 minus CVO2 on both sides to get rid of it on the left side. So we're left with the shunt fraction equation, QS divided by QT. The numerator has CCO2 minus CaO2, which is the oxygen content of the blood flowing through the pulmonary capillaries minus the oxygen content in the arterial blood. That difference represents the oxygen-poor CVO2 blood coming from the shunt and mixing with the oxygen-rich CCO2, thereby causing CaO2 to fall. And the denominator is CCO2 minus CVO2, the oxygen content of the blood flowing through the pulmonary capillaries minus the oxygen content of the venous blood. This value isn't affected by the shunt at all, since oxygen-rich CCO2 and oxygen-poor CVO2 blood coming from the shunt represent values before the two get mixed together. Alright, as a quick recap. A shunt is a rediversion of blood from its usual path through the pulmonary circulation. Shunts can be physiologic or pathologic. They can also result in a left-to-right or right-to-left diversion of blood across the heart. The amount of blood that flows through a right-to-left shunt can be calculated using the shunt fraction equation, which is based on oxygen content of the blood.